Well, I guess I owe some people in this room an apology. I mean, Marcello, I think, and Leonid, they have heard me speak about this. Well, maybe someone else. Well, on the other hand, someone very wise told me once that never apologize like this because he said, do you really think that you impressed people so much that they still remember the rubbish you were talking about last time? Anyway, so I will be talking about estimates for the number of negative eigenvalues of a two-dimensional Schrödinger operator. So let me start with, well, the first general case, any dimension. So we have just the Laplacian in the whole space. By easy Fourier transform thing, you can see that the spectrum is just a positive half line. And then you can see the Schrödinger operator. You have a non-negative potential, so you subtract. In general, it may move the part of the spectrum to the left, so you might expect to have, a non-empty intersection. So there will be negative numbers there might be negative numbers in the spectrum, and you would like to estimate the number of those. So you want to estimate the number of negative eigenvalues. So I will try to, I don't want to go into the conditions under which the operator is self-adjoint, and I don't want to go into those difficulties. So basically, the thing we're talking about here is this. So you look at the quadratic form of the operator. Well, we can say take this domain, which means that both integrals are finite, and you look at those subspaces in the domain on which this quadratic form is negative everywhere apart from 0, obviously. So you look at all such subspaces and look at the dimensions, and the maximum dimension is the number of negative eigenvalues. I mean, when I say the number of negative eigenvalues, I mean this. So if your operator is self-adjoint, then this is indeed the number of negative eigenvalues, provided this number is fine. Okay. So the well-known case, the well-understood case, where the underlying space is at least three-dimensional, you have this famous estimate. So the authors here are given in alphabetical order rather than in the order of sort of historical order. Okay, so, and this is a very beautiful estimate, and this is a kind of natural, correct, and a good one. What do I mean by that? So, well, first of all, so if this integral is finite, then, well, obviously, instead of v, you can consider v times a constant. And then from that integral, you have this, and this is a correct semi-classical order of asymptotics. And then if you have this, turns out that you actually have this asymptotic formula. So if you have your potential in this direct space, then not only you have the order estimate, you really have the leading term of this estimate, and you can see that, well, this is, well, the integral we have in the right-hand side there is actually there for a good reason. This is exactly the leading term of the asymptotic. So, and also, if you know just that you have the correct order in the semi-classical asymptotics, then necessarily the potential is in this Lebesgue space, and then you have the estimate and the asymptotics. So everything fits nicely together, and this is, you can see that this is sort of the natural language.
Just a small question. What a priori information do you need about V to have this statement?
This statement?
Yeah, the first three lines. If and so on.
So if somehow you know that this happens,
yes, but
so suppose locally integral.
For some class of potential.
Which is the initial assumption on V?
Well, suppose locally in L1, say, something like that. I might be not entirely correct here, but this is sort of not the main issue here. So I would you can say that it's
So
sort
you
of,
want that the form is well defined,
Yeah.
C0 infinity.
Yeah. so you have, I think you have to have just locally L1, but I might be wrong. So anyway, so under very minimal restrictions, you have this result. So this case where the dimension of the underlying space is at least 3 is well understood. Now, if you take, so the power here is, as you can see, is d over 2. So if you formally take d equal to 2, two-dimensional case, then, well, formally the estimate should be just the integral of v. And so, so this estimate, however, cannot hold. And there is a sort of trivial abstraction to this, is that it's well known that as long as you take, I'm talking about for the whole of the talk, I will only talk about non-negative potentials. So as long as you know that your potential is non-zero, it immediately kicks out of the spectrum at least one negative eigenvalue. It can be arbitrarily small. So therefore, suppose you have this estimate like this, you can have this integral very small, so the right-hand side will be less than 1.
But constant can be big.
But, okay, whatever constant you have, take the potential whose integral is smaller than 1 over that constant, so the right-hand side will be less than 1, and nevertheless, the number of negative eigenvalues is at least 1. So this is a trivial abstraction to this one. More serious is that, suppose I put this plus a constant to take into account exactly this effect. So, but turns out that no, you cannot have estimate not just constant plus the integral of v. You can put any weight you like, as long as this weight is bounded in a neighborhood of at least 1 point. An estimate like this cannot hold. So there is no L1 kind of estimate for the number of negative eigenvalues, and this result by Grigorian and Nadirashvili, it's not a difficult result. That people understood that this is the case. Maybe without the weight, but kind of they simply wrote it very nicely and sort of. So this is not a very difficult result. However, the next one is a beautiful result. It's very, very non-trivial. So this is by Grigorian, Nitrusov, and Yap, which says that you have a lower estimate, and this is a very, very deep result. It's a beautiful result. And also, by the way, I stated it like this, and for this talk, that's fine for me. But actually, what they proved is not just for potentials in L1, it's for measures. And for some reason, the fact that measures are allowed here is important for me at the level, not for the results I'm talking about today, but it was one of the main points in the motivation why I came to this project. So what you see is sort of this case is different. Now, if the potential, I'm talking about still two-dimensional case, if the potential is nice, there will be sufficient conditions later on in the talk, but if the potential is nice, then you have, well, the semi-classical asymptotics, and you have a formula that resembles the formula in the higher dimensional case for the asymptotics. However, the situation is not quite as straightforward even here as it was in the multidimensional case, because what may happen is that, say, remember, if you had this, in the multidimensional case, you had the asymptotics. In 2D, this is not the case, so you may well have this, but you might not have an asymptotic formula, and even worse than that, you may have a situation where you do have this limit, but it's different from what you expect it to be. So everything is, so it's a genuinely more complicated case. Now, and one of the reasons why two-dimensional case is different from another, it depends, I guess.
It just works like that.
Pardon?
It just works like that.
Excellent, excellent. Wow, I'm impressed. So, just a sort of explanation why this two-dimensional case is different, I guess, different from people, different background. If you're a hardcore spectral analyst, probably your sort of intuition would be different from mine here. So one of the sort of trivial things is that if you take, you are trying to take the inverse, say, for the Laplace operator in Fourier terms. So this thing is integrable in three-dimensional case in high, and it's not integrable in two-dimensional case. So this is one. But another thing is which I guess will motivate what we expect to have is just embedding theorem. So in order to have, say, finitely many eigenvalues, you probably want to have this term somehow dominated by the energy norm. So I suppose you want this term to dominate that one. Okay? So suppose you are trying to see where you want this potential to be in order to make sure that the interval is finite. It's just the Hölder inequality. So suppose this is in some, suppose you want to have this in some LP. And then, say, suppose you are taking, so this will be in, say, I just want to check my notation there so I don't embarrass myself here. So, yeah, suppose you have some LQ. Now this LQ will come from just Sobolev embedding theorem. I just want to check the exponents here. So this thing will be, because it's squared, it will be in the space LQ over 2. So in order to use Hölder inequality here, you will need to have 1 over P plus 1 over half of Q. So it will be Q equals to 1. So therefore what you will have, it will be 1 over P equals 1 over minus 2 over Q. So this is a kind of natural restriction on V, just a naive one. And then when do you have, so on the other hand, you have U in W1, 2. And then, so you want to see the Sobolev embedding theorem, so it will be, then this will be in LQ. If you have so 1 minus d over 2 should be equal, well, the greater than or equal to, but let me take equal, the best exponent, it will be 0 minus d over q. Okay, so if I now multiply this by 2 over d, I will have 2 over d minus 1 equals 2 over q. Am I doing this right? Minus, yeah. Thank you. And then, so 1 over 2 over q is what? So we have, so 2 over d is 1 minus 2 over q. So from here we conclude that 1 over p is 2 over d, or in other words, p is d over 2. And well, this is obviously not the proof of the estimate I showed you, but it sort of explains why you would expect d over 2 in the power, in the estimate in multidimensional case, and sort of explains why this doesn't work in two-dimensional case, because in two-dimensional case, you would be exactly having the situation where you want to embed this into infinity. And this is exactly, so if you take this q there, so you will have exactly, say, see what is, So look at this. So when d equals 2, you have 1 here equals 1 minus this. So q should be infinity. And this is exactly what fails here. So 1 over 2 just fails to be, so W12 that just fails to be embedded into R2. And it is embedded in all LPs with p less than 2. So somehow you understand that what you will expect, one would expect an estimate where instead of the integral of v, so instead of the integral of v, you have integral to a higher power. But obviously this is not going to be optimal, and what you kind of intuitively expect to have is the following. So this embeds in all LPs, but this is not the best possible variant. So there's kind of a gap between LP with p less than infinity and L infinity, and what fits in there is the sort of exponential classes. And therefore, what you expect to have there, it would be something that is between L1 and any LQ with Q greater than 1. So one would expect that what you expect to have there is something that fits between it would be L log L. So when you multiply the function by its logarithm, and then this is what you expect to have in the right-hand side. And this turns out to be the case. And basically, the talk is, well, more or less about this. But I wasted that much time because I wanted to motivate this thing that I will have to have, if I try to minimize the restrictions on V, and this is the name of the game in this business, so I will need to look at the classes where what is integrable is V times its logarithm. So this is the message here. Now, why would one be interested in this case? After all, it's not physically the most interesting case, while it's two-dimensional. I guess the honest answer to this is that, look, it's a difficult case, it's a challenge. I mean, there's something that, well, it should be easier, right? So you have low dimension, and you can see that, well, top people in spectral analysis were trying, we're working on this problem. So if they find it interesting, surely it must be interesting. But so my own motivation is slightly different. You can see that this is a linear two-dimensional problem, and my motivation, surprisingly enough, came from one-dimensional non-linear problem. So it was joint work with John Toland. We were working on Stokes waves, and we wanted to have an estimate of a Morse index of a particular problem. And then it reduced to a one-dimensional problem where instead of the Laplacian, we had think of square root of Laplacian. So where we had a pseudo-differential operator that was the derivative of the periodic Hilbert transform. Periodic, by the way. That's it's exactly that's the only time I will use the word periodic in this story. So it was so the symbol of this operator was just mod of psi, and then it's 1D operator. We needed an estimate. Actually, what we needed, John proved anyway, but he used, in the proof, he used a lot of information that we had from nonlinear problem. And we both understood that it was a linear problem. We wanted to have a purely sort of linear argument along those lines. And we could not do it. I asked many people, then Leonid knows the story, so I offered a good bottle of wine for if someone solved it, and then no one solved it, and then I offered, Leonid challenged me that I offered a bottle of Chateau Latour for a person who solves this. And then it still didn't work. And then actually what we needed was a low estimate there. We were not after an upper estimate. We wanted a low estimate.
Should have 10.
Pardon?
10 Chateau Latour, not 1.
And then turns out that it was a very risky proposition because what happened eventually, then we realized that 1D, it was like Dirichlet-Neumann operator on the circle. And then you could reduce it to 2D problem. But then for 2D problem, we had just the Laplacian plus a potential that was not locally, it was not an L1 function, it was a measure supported by the unit circle. But at that point, we wanted to a lower estimate, and actually, eventually turned out that, remember this result. So the whole of it turned out to be a result could be easily reduced, so therefore kind of eventually I didn't buy that bottle of Chateau Latour because somehow kind of it wasn't clear. I have to say that at some point Netrusov told me that, look, I'm not interested. At that point probably that was not Chateau Latour, it was just a bottle of wine. He said, look, I don't want a bottle of wine. Buy me a bottle of Grey Goose French vodka, and I do it, he said. And somehow I said, yes, okay, but he could not be bothered writing it down, I suppose. But looking back at it, I think he really was in a position to get that bottle of vodka, I think. But he kind of was never bothered to write this down. Anyway, so but when we sort of solved that problem, then you sort of get greedy, you want to have an upper estimate as well. And the upper estimate is, well, this is where I realized that these people were working. But had I known from the beginning, I wouldn't have touched this problem. I mean, I don't expect to succeed when Netrusov, I don't know, Nadirashvili and others could not. So, but at that time, I was already kind of heavily involved. It was too late to think about it. So, as you can see, that there are two periods where people were trying to sort of get good estimates there, and then you see that there is a gap, and somehow you can see that there is a sort of renewed activity. Yeah, and one of the reasons for this renewed activity is that in the middle, theoretical physicists, proper theoretical physicists got involved, and they made progress on the radial case where the potential depends just on the modulus and not on the direction, and they made a conjecture. So, and people were, well, trying to prove this conjecture without success, and actually Molchanov and Weinberg, they came very, very close to proving it, but still, so under certain restrictions, additional restrictions, sort of proved it, but no, they didn't completely solve. Now, and I would like you to just pay attention to this one. It's Solomiak's paper in 1994. That's my favorite in this business, and I think by the end of the talk you will love it as much as I do, okay? Right, so as I told you, we expect to have estimates in terms of something that lies between L1 and LP spaces, so this is where we need Orley spaces. So the next 2 or 3 pages will be a brief introduction to Orley spaces. So basically the idea is this. So instead of integrating the modulus of f to some power, we just stick it into a more general function and try to integrate this. So that's the idea of the Orlich spaces, but there are at least 2 sort of difficulties one needs to address here. One is that if you have type which grows very rapidly, for example, exponentially, and remember, so this embedding you don't embed it into an infinity, but this is, say, you embed it into exponential classes. So for one of those exponential classes, if you just take your space as the space of functions for which this integral is finite, this is not a linear space. Because if you multiply your function by 2, you might be squaring your exponential, for example, so therefore you don't expect. So this might not be a linear space. And another one is that when we will need the norm, or a norm, there. When you have LP, so this is P's power, and then you have the root, P's power root there. But how do you go about this when you have a sort of more general function? So you need to look at these 2 things, but obviously sort of very classical stuff. So what you do is, well, first of all, what are those functions for which we consider Orlich spaces? So what you are talking about continuous and convex functions, and also those functions, they decay faster than t at 0 and grow faster than t at infinity. So this is what you request. And also, this one is, so those functions, n functions, they come in pairs. You don't need to spend too much time trying to sort of understand what this formula is, and if you've done sort of convex analysis, you know what this thing is, but this is just, think of this as the dual functions, like LP, LQ. So if you take one of those functions and you eventually will try to look for the dual space, it will be a different Orly space, and it will correspond to this function. So if your original function was psi, then the dual will be this phi. So you can think of in terms of this. So
This is
classical
French,
example.
At least we call it Legendre.
Legendre, that's Legendre transform. Yes, that's exactly. Yes, that's exactly Legendre transform. Yes. So if you have so for the classical function LP LQ, and remember Pastor, he gave a talk at Queen Mary, and once he said the joke, how to decide whether a person is an analyst or a probabilist. And the answer was that if 1 over p plus 1 over q is 1 for you, you're an analyst. If p plus q is 1, you're a probabilist. Right, so the two functions, the dual functions, that I will be most interested in are this one. So again, there is no need to remember exactly what they are, but so I'm talking about integrability, so I'm talking about where function is large. I will be substituting it to here, but you can see that at infinity it grows like t times log t. T log t, and this is exactly what one expects to have in that business. So this is the function to sort of remember. That will be the main function. And yeah, and then when you have a pair of those dual mutually complementary n functions, you can define your Orly space either sort of Han-Banach really. So either using Han-Banach, so the norm will be the supremum of this where G satisfies this condition, or you can do it more explicitly without involving the dual function. You just look, well, you hope that for large enough k, kappa, this will be small enough to ensure that this interval is less than or equal to 1. And then you look for the smallest kappa for which this is the case. And this is another way of defining a norm, and these norms are equivalent. And these norms are equivalent, and the space is just a set of functions for which these norms are finite. So that's the Orly space. Now, one thing, by the way, important about Orly spaces, which is of no relevance for this talk, but still a useful property of the class of Orly spaces, that if you have a function in L1, it will belong to some Orly space. So it's not just integrable. You can just kind of not quite rise it to power p, but you can make something larger than just the modulus of the function. It will still be integrable. So every integral function is in one of those Orly spaces. Anyway, so this is Orly spaces, and the thing that is important for today's talk is that Solomek in his paper introduced an equivalent norm. So remember in the norm where I showed you at the beginning, it was 1 here. He suggested to look at this norm where you just put the measure of the underlying set. Well, obviously for a given set, that's an equivalent norm. You just change the constant here. It's, well, quite easy to prove this two-sided estimate, but the reason this norm is more convenient because it scales better. So suppose you, I will need to look at the circular annuli, and so then they are just, each one is obtained from another one by just multiplying by number, and then you want to see what happens to those norms when you do that. And Solomek's norm has the right scaling, whereas the traditional norms do not. So this is a better norm for our purposes. So this is, I guess, what I wanted to say about Ulrich norms, and I think that yeah, this is the most technical one. So what we will need to do is the estimate traditionally sort of comes from subdividing R2 into circular annuli, but there are two families of those. In one family, so you have just the these are exponentially growing, and you don't have well, yeah. And sometimes you don't want to look at the negative ones that shrink to zero. You just look at the ball. And here you have something that is not exponential; it's doubly exponentially growing. So this is something that is traditionally used in this business by Solomon, by Biermann, but by others. So this is probably the most technical page here. So these are the annuli, and the estimate. So what you do is, well, in all estimates I will be talking about, there will be two types of terms. So L1 norm is not enough for the upper estimate. So we know. So we need to have something larger, and there are two ways of going about this. One is that you multiply V by weight, a logarithmic weight, but this on its own will not be enough. Remember the result by Grigorian and Nadirashvili that you cannot do it just by putting weight there. You cannot have an estimate of this term. So you will also have terms of different type where you make something that is larger than L1 norm at the expense of considering slightly higher Ulrich norm. So this is L log L norm, and L log L norm is the darling of all harmonic analysts. This is where sort of, if you say, most operators in harmonic analysis, they don't go in from L1 to L1, but they go from L log L into L1. So this is L log L space, but well, it will be convenient for us to work with the norms introduced by Solomon for the reason I told you. So remember those annuli, you just multiply each one by E, and you want to have a good control of how the norms scale, and this is why we have those norms. And this is the result by Solomon. This is the estimate, and so we have two types of terms. So you just add L log norms of the potential or the annuli, and here you take the sequence of those numbers, those integrals, and you take the weak L1 norm. So it's the weak L1 norm here. So that's the definition of L1 norm. And for some reason, well, I guess I know the reason, this estimate is very kind of an unloved estimate. So nobody loved it, nobody liked it, including Solomon himself. So in a sense, it's sort of an unloved child, because, well, if you look at this term, somehow people could see that this is a natural term to have, because, well, this is not, I mean, L1 norm we know is not enough. We expect to have L log L norm, and this is exactly what it is.
Sorry, and what is omega 0, omega n?
So these are the annuli.
Okay.
So for Ulrich norm, we take annuli that scale exponentially, and for the weighted L1 norms, double exponentially. So you can see that, well, this is something that is natural. Now this term, I think the most sort of what people were unhappy about, this is probably what at the border of what people would accept. And this was, I guess, was beyond it. I mean, you're estimating negative numbers. Come on. The weak L infinity, L1 norm, weak L1 norm of the sequence is clearly artificial. It's here because of the method. It's not because it's not what it should be. So it's kind of, you can see it. I mean, just your common sense tells you that that's a wrong one. So therefore, although
Does it behave semi-classically?
yes, you can. Yes, it's if two things are finite, then you have semi-classical. It scales right. It scales right. Yes. So, but well, anyway. So kind of, I guess this was it. Now. So, and again, it's not a kind of estimate a physicist would like. So now this brings me to the conjecture by physicists, Curie, Martin, and Wu. And the idea, I guess, was, although I've seen their paper, but it's not that easy for me to understand. I mean, what physicists when they sort of arguments. So I guess the idea was the following. So think of this sort of, you have this you are subtracting non-negative potential. So the potential tries to kick out from the spectrum negative eigenvalues. So kind of the stronger that potential is, the more it will kick out, right? And somehow you think that if you make it radially symmetric, the potential, so rearranging, it should be stronger. It should kick out more eigenvalues than a non-symmetric one. And it kind of seems reasonable. And therefore, so what they did, they suggested to look at the spherical rearrangement. So of a potential. So this is the new potential that is radial, doesn't depend on the direction. And it's sort of the distribution function of this is the same of that of the original potential. And by the way, this is, I think when Martin gave a talk at the physics conference, obviously he realized that sort of spherical rearrangements were probably not something that would be in the background of every physicist, so he tried to explain it there. And the conference was not very far from Mont Blanc. And so this is how he explains. So you take sort of the map, and you look at the level sets on that map, and then you just make them circular. And you have a new mountain, so which is perfectly symmetric, and basically, well, it has the top over the origin of code. And when I read that, I realized that the only word I didn't know what, I mean, the meaning of those was this. And apparently this is the map that was the first to map the vicinity of Mont Blanc. So here it is. So if you are as ignorant as I am, so this is the map. Anyway, so, and their conjecture was this. And you can see that this is kind of, the way it looks, it's closer to the estimate that we have in multidimensional case. You have just integrals without all this kind of strange, weak L1 norms of the sequence, etc. So what you do, you take, you integrate the function against log. So this basically tells you, in a sense, it kind of measures the behavior at infinity, because log is, see, it's log plus. So for x less than 1, you don't have this term. So it's just at infinity. And this one says that, remember this function, it has a peak at 0. And this, you don't just integrate. If you didn't have this term, the integral, this is exactly the integral of v, because it's just the rearrangement, measure present measurement. So, and here you are putting large quantity that grows at 0. So basically, so you're kind of restricting the growth of the function at 0. So this is was the conjecture, and then 1 year later, they even specified the constants here. Just the slight difference between these two inequalities here in that paper, they looked with log with a plus here without. So for small values of x, it might be negative, but then it's controlled by the other term, etc. So the equivalent, and they conjectured that well, the constant should be this. So this, they had factors to pi. I wrote slightly different. So basically that this should be 2, this should be 1, and that one, they had this 2 square root of 3 there, because that was, again, the motivation I think was coming from the radial case. And in the radial case, that was the best constant known at that time, but they said that, look, the only thing which one can probably improve here is this constant. And that was indeed later done by Solomiak and Laptev and Solomiak, who showed that so this constant is 1. So if you can prove it, I mean, you cannot improve those constants because these are the constants that you have in the radial case. But whether you can have it for all cases. And so what they said is the following. So they said that, well, 46, I think, is the estimate, just the last estimate I showed you. That they said that, well, it's probably very difficult to prove. Now, if you take this as a statement that difficult to prove it with the explicit constants, then this is still correct, because at the moment there is no way, I think, that one can really get hold of those constants. On the other hand, if you...
Not even one of them.
No, not that I know. So but if you are happy with an estimate without explicit constants, then it's true. That result is true, and so this is the result. Well, it's written differently, but again, you have a term which you have V integrated against the weight, and just this L of L known there, Orlich norm, and this is the estimate. And this estimate is equivalent to the conjecture by Curie maximum rule conjecture. And the idea, when I sort of got this estimate, I didn't quite realize that it might be sort of, it proves the conjecture, because, well, here you have an Orlich norm, and there you have sort of rearrangement. It was actually the paper by Molchanov and Weinberg that sort of, there was something, there was a connection there. And then it turns out that, wow, it's a well understood connection in functional spaces. It goes back to Bennett. He didn't have explicit constants, but these are constants, and this is the constant from my paper, but they are not, I don't think they are anywhere close to sharp. Just some constants. So as you can see, the Orlich norm, well, estimates above that rearrangement, spherical rearrangement integral, and above that term plus just L1 norm, and that L1 norm is there anyway. So as you can see that this settles the conjecture, and well, kind of let me just estimate, let me compare this estimate.
Just a second. Your estimate is bigger than the conjectured one, or do you also have the inequality in the other?
Yeah, we have this inequality as well.
And this gives you the...
Yeah, and they're equivalent.
Sorry, I didn't see the...
Yes, they're equivalent. So, and this solves the problem, and then it's sort of natural to compare the estimate, this estimate, with the estimate that Solomek had. And I have to say that Solomek and Biermann, they had made comments about comparing various estimates, including, say, Solomek's estimate with something else, with other. They said it's kind of difficult to compare those estimates, and it sort of is indeed difficult. So let us look at, so remember, in all estimates, you have weighted L1 norms and something stronger, say Orlich norm. So let us see the first type of terms. So this is what Solomek has, and this is what is in, so say in my estimate. So as you can see, what I have is larger than what Solomek has. And actually, it is indeed larger, so it's not what you can easily, have is that you can have a function and potential for which what Solomek has is finite, where this integral is infinite. So there, Solomek's estimate is better. So on the other hand, if you look at what Solomek has there, as far as Orlich norms are concerned. So first of all, remember he had averaged Orlich norms where the constant was the measure of omega. And now we're talking expanding sets, so it was large constant. So therefore, that was larger than if you put just a traditional norm. And then this is sum of norms of all those annuli is larger than just norm of the whole space. Think of LP norms. Just think that this, I'm talking about LP norms of those annuli. So you have, this is obviously larger than that. And again, what you have here is, in each of these inequalities, you have exactly sort of, you may have a big difference. So you can have a situation where this is infinite, whereas this one is finite. And you can also have a situation where this is infinite, but the right-hand side is finite. So you can pick up infinities on both steps. So therefore, one term in Solomek's estimate is better. The other one is worse. So, but if you compare this to, say, I think that the estimate that I have is by far the best looking one in the business. It sort of looks nice. It solves the conjecture. So surely it's better, obviously, and well, I think I should have left it there. And I think I should have stopped my talk there. But I made a big mistake. I decided to come up with an example of a function for which what I have in the right-hand side is finite, whereas for what Solomon has is infinite. So I tried to construct an example, and like I said, it was a big mistake. Turns out that Solomon estimate is strictly better than what I have. Strictly better. So what happens here is this. Think of the terms that Solomon has. Remember, there are two steps. One going from average to non-average. Yes, this is larger when you have average than this norm. By whatever it is larger by, it's controlled by L1 norm. So it's one step. The other step was that, remember that I said that, well, this sum is larger than this norm. It is. But whatever it is larger by, it's actually not just V integrated about log, it's V integrated about against double log. So, yes, that part in Solomon's estimate is larger, but the difference is controlled by the other part. So therefore, Solomon actually sort of proved the conjecture 8 years before it was stated. Okay? So, like I told, I should have stopped there. So now let me show you. When do I need to stop? Because I think it's.
Yeah. So how much time do you ask for?
2 hours. No, seriously, we start.
Well, I don't have 15 minutes. So
Yeah, okay.
Russian style.
10. So now let me show you. So again, so I guess the best known estimate at this point is where, remember those annuli I had just Orlich norm that was two-dimensional. Just kind of look at Orlich norm there. So what you can do is, Orlich norm is stronger than L1 norm. So what you can do in those annuli where you had Orlich norm, you can do Orlich in the angular direction and have just L1 in the radial direction. So this is a weaker norm. It sits strictly between L1 norm and the two-dimensional Orlich norm. So this is basically what it says. You do so you go to polar coordinates. In the angle you have Orlich norm, the same Orlich norm, but then in the radial direction just do L1 norm. Okay. Otherwise we'll have again the same weighted integrals. And now what changed compared to Solomon's estimate in that Solomon had two-dimensional and average norm. So here you have just this, and this is the result. So now writing this term with weighted integrals in this form, I picked up from Grigorian and Nadirashvili's paper, but it goes back to Pirman and Solomon. Although Solomon is not particularly fond of this way of writing it, although, like I said, it goes back to their paper. So, you see, when I first saw this, I sort of thought, look, it should be large, because think of this as L1 norm. You want this to be convergent. You are putting square roots there. Square roots are larger for small terms, so you're kind of asking for a worse series to be convergent. However, the key thing here is that you are not taking all the terms. You are taking them starting from some size. And then in that case, what you have is that this thing, for any constant there, is estimated above by the weak L1 norm. And well, actually, I mean, obviously you can have a situation where this is finite, where this is infinite. I mean, just simple things. Think of all the terms that are simply smaller than this C. That will be 0, and the weak norm will be infinity. And another one, so anyone who has done Hardy inequalities, well, can kind of guess where this form 1/4 comes from. Oh yeah, by the way, so it's about how these things scale. this norm, this square, if you put alpha there, and then you have semi-classical asymptotics only if and only if this weak L1 norm is finite. And you can have other regimes, so basically you can translate any kind of more or less any kind of asymptotics of those terms in terms of distribution function for that sequence. But back to those 4 1/4, so kind of one can think that kind of optimal. It's something from Hardy inequality, but no, it is not. It's just sort of a I don't know, marketing trick on my side. So actually, unfortunately, there is a bad estimate where it has nothing to do with 4 in Hardy inequality. So simply you have those numbers. That's it. Okay, so this is the inequality that we have, and yeah, and then you can also, as a consequence, this is some people very often, Solomon, many people, they kind of look at this potential. They just extract the radial part when you integrate over the angular coordinate, and then you have non-radial part. So and then you can have this estimate that where in that Orlich kind of norm you have just non-radial part of the potential. So and again we sort of keep getting this, and remember I started saying that the people didn't like it because it's kind of artificial. And well, one can prove the following estimate that if you have those, I mean, I don't need to read it for you, so the estimate from below for the number of negative eigenvalue in terms of those things. And then from this estimate, you have that corollary that if you can finite number of negative eigenvalues, then this sequence has to be bounded. But the question about correct semi-classical asymptotics is this, that under no additional restrictions, you have asymptotics if you have this asymptotics, then this term is there for a reason. It's not artificial. The fact that we didn't like it, it's a reflection of Solomon or whoever we didn't particularly like it. It was wrong. We have wrong taste. But this is there. Well, it's not artificial. It has to be there. It's in the upper estimate, and it's also if you have this, you have to have it. So that's the second time that's sort of what surprises me. So that estimate of Solomon A turned out to be stronger than that famous conjecture, and B, the worst part of it, it's actually a necessary thing there. And just why one should sort of look at this thing, it's with the coupling constant rather than with the potential itself. People know this for, I mean, in a multidimensional case, which is well understood, you know that's for one potential, there is also the coupling constant matters. And so what, yeah, by the way, one thing is that if you want to have, so in Solomon's estimate, we have 2 parts, right? So in all those estimates, weighted part, and I think I just convinced you that what Solomon has, whether you like it or not, is the right one. As far as the Orlich is concerned, well, I showed you something that is weaker than Orlich. That was Orlich in one variable and just a one in the other one, so it cannot be optimal. But if you want to have Orlich estimates, then you cannot take anything better than B. You cannot. This is optimal. L log L is optimal. If you have another Orlich space where the norm is weaker, so you have small upside, then you cannot have an estimate like this. It's like, again, sort of an improvement of Grigorian Nadirashvili result, which says that no matter which Orlich space you take, where the norm is weaker than in L log L, you cannot have an estimate by any weighted integral of V plus that Orlich norm. So that is optimal in the class of Orlich spaces, but Orlich spaces might be the wrong language for this. And just the final thing is that what I just started saying that, what you may have is that obviously it's true in multidimensional cases as well, so you may have a situation where for some coupling constants, the number of negative eigenvalues is infinite, and then you go over the threshold, it becomes, so it's finite, smaller ones infinite for larger ones, and then you can have for alpha equal to 1, this may or may not be finite. And if it's infinite, it can grow, the number can grow. I cannot prove any given growth there, but I can prove arbitrarily fast or arbitrarily slow. This I can prove. So for example, so this is the last result, and I stop here. So you can have a potential where the number of negative eigenvalues is whatever you like, finite, and then when you increase the coupled constant over 1, it immediately becomes infinite. So you can have the situation where this is infinite, and then the number of negative eigenvalues grows arbitrarily fast. So you give me any sequence that converges to 1, and then I can construct a potential such that between those numbers, between those alphas, coupled constants, the number of negative eigenvalues jumps by whatever you like. So you go as fast as you like. On the other hand, you can also, so this is a condition which means that alphas converge to 1 very, very fast. I think it's faster than exponential. So this condition means that they go to 1 very, very fast. If you have those, so if this is satisfied, meaning that alphas go to 1 very fast, then you can construct a potential that it grows very slow. Number of negative eigenvalues goes very slow. So you increase, you go very fast to 1, and yet it increases by 1 at any moment. So that's all, I think. Yeah.
Okay, thank you very much. I want to make a comment. It was ages ago, 10 or 15 years, Zhenya and I, we attended some talk by our colleague. And Zhenya said that any analytical talk that has double logarithm in it should be a great talk. And by these standards, this talk has not just double logarithm, but also double exponentials. So
What are you, wait. Yeah, look
Yes.
at this. Yeah, double.
yes, precisely, and double exponentials. Yes.
Yeah, okay.
Right. Are there any questions?
And just this A. Martin is André Martin, or what?
The one
this
who
is
worked in
this
CERN
is
in the theoretical.
in Switzerland.
Yeah, that's the one. Who was, I think he was the head of theory group there. And by the way, look, as a mathematician, we love to sort of justify our existence in usefulness, saying that, look, physicists, we do something that is of interest to physicists. And this is a conjecture, it's not something that kind of we attribute to them. This is conjecture from their paper. They repeatedly stated that conjecture. So I sort of solved it. I sent them, all of them, email, expecting at least, a lukewarm tap on the shoulder, saying, yeah, it's okay. None of them replied, because for them it's kind of ancient stuff. No one is interested in this stuff anymore.
I suppose André Martin is 70 or 75 years old.
Yeah.
Huh?
But some are younger, so.
He's no more.
But then, I had the feeling that simply kind of things just moved on. They are not interested in that stuff anymore. So, okay, you proved something. We knew that was right anyway, so why?
Because I remember in the 80s, I was proving with Didier Robert some semi-classical picture on this, and I got a letter of André Martin saying that he has done this 10 years before, something like that.
Oh, so, well, this is a set. Well, no, I'm sure that way it works. But
So has he really proved it 10 years before, or
No,
has he just?
he's a physicist.
Well, yeah. So
He
on
knew
physical
that.
level, he knew that.
Yes, but sometimes he claims that he has proven so.
But do you think he has proven it?
no.
I have not verified the proof, because
Okay.
I don't know. Maybe, yes.
He's a physicist.
Okay. Further questions? Comments? Sergey?
So for the shrinking Rosen in 2 dimensions, there was a lower bound found, right? So
Yes, that's
fine.
a lower
Is it
bound.
known in bigger dimensions than such a lower bound?
I don't think that I don't
So
think
in
that
this case, 2 dimension is better studied than.
yes, but we don't have the sort of closure. You see, what I kind of, It's not Mem, it's Solomon. We have discussed with Solomon and others. So you need to have some quantity. So one thing is that the weighted norms, and this is weak L1 norm, now we know it's there for a reason. And then you also have something that should be kind of like, not quite Ulrich norm, but something of that type. We know what the properties of that quantity should be. One property is that you want to have an estimate. So this is less than equal to some quantity involving V, and say this norm. This is about pointwise multipliers, and Mazia has necessary and sufficient conditions for this inequality. And those are in terms of capacities. So that well understood, this estimate is well understood. Now what you want is to have a quantity like that, which you put in the right-hand side there. It should scale right. This is why Solomon introduced average norms, and it should be superadditive, meaning that if you have that quantity, so you have a domain, you subdivide it into non-intersecting parts. You take that quantity for your function, calculate it for each part, add them together. It should be less than or equal to that quantity of the whole domain. So if you have a quantity that satisfies these three conditions, you can use the machinery, and then you have an estimate for the number of negative eigenvalues. Somehow, what that quantity is in the pointwise multipliers theory, sort of capacity that doesn't have the other two properties. And somehow no one has come up with, I think, I at some point I discussed this with Mazia, but I guess I was not ready then. So if I go back to him now, maybe I should, and I will, I guess, and talk to him again, he might show that. He may know the answer. He'll say, well, you do this, and that's because we understand what that property, what the property of the quantity should be. He might know the answer, or might solve this problem. So.
But you have a theorem that whenever something satisfies this property, then you have estimates.
Yeah, I mean,
something.
we sort of pushed it. We sort of now you have Ulrich in one direction, L1 in the other one. You know that L1 is not enough. You know that L log L is optimal for Ulrich. It's kind of, in a sense, natural, but it's not the kind of inequality that you have in high-dimensional case. If you have the right semi-class asymptotics, then that norm should be fine. So ideally, we would like to have, this would be the complete solution. So you have an estimate, an upper estimate, such that whatever you have in the right-hand side is finite if you have the right, if you have the correct order of semi-classical asymptotics. The first term, the one that sort of seemed to be artificial, is the right one. So now we're talking about the term that people felt it was better, so to speak. It was more natural. We're talking about something like Ulrich norm. And there you need, that's not optimal. And by the way, in a sense, a surprise was that, look, when the weighted norm, remember it was kind of expanding, doubly exponentially expand annualized, you single out the point that is special for you, 0. But the whole thing kind of is translationally invariant. Well, why should the potential care about 0? Maybe one kind of should take a different point. And then your condition seems to be on the choice, depend on the choice. Well, it's a necessary condition. So,
well, but when you go verify, it doesn't matter whether you start from.
It seems to be this effect. But it doesn't go just to infinity. It also zooms to 0. But I think probably that is dominated by kind of Ulrich or whatever. I don't know.
Just there were not a paper by Kondratiev Egorov at some times about this subject, no? In we weighted norms.
Could be, but no, maybe not about this because, well, I'm not an expert on this. I accidentally found myself, and I think that sort of maybe I am for advice to younger people. And those people, A, were expert, and B, by far better mathematician than I am. So under normal circumstances, I wouldn't try. But sometimes you're free. You know what happened is that they all had their own techniques. And I felt free to borrow from, and all all the results I proved is exactly this. I took something from Grigorian and Nadirashvili, I took something from Molchanov and Weinberg and from Solomiak, and then when you sort of, if you don't have this sort of your own technique to prove that it is better than anyone else's, then you just take other, when you don't have your own ideas, you just borrow from other people, and that's the strategy.
Further questions? Okay, let us think.